years, a few hundred years before Thomas Hales took this problem and turned it into some kind of effectively deductibly written system of theorems, which ended up with a complete resolution of this Kepler. It's such an intuitive thing to comprehend. Like we look at the picture, we as humans, and we can immediately see the essence of the theorem, right? Like every child could comprehend what is exactly the point of this theorem, like what we are trying to prove. But somehow the actual formal mathematical proof is extremely intricate, extremely complicated. We need to build a lot of notions which are not very intuitive, and to actually organize it into a convincing proof. That was a feat that was just very recently achieved. It was actually done in a formal system. I'm going to talk about these formal systems. But I want you to keep in mind this big gap between formalization per se, so just a collection of sentences, that somehow every single step can be completely trivial, and somehow organizing this system of formal sentences that will in the end actually derive a precise sentence that corresponds to the intuition that we have in the picture.
Hợp tác quốc tế cũng nhiều nữa, nhiều
Okay.
hơn chữ bộ môn đó chị.
Oh, someone asking a question?
Tại vì nó tính cái số giờ chứ giảng.
All right. So I think the next example I want to mention is the four color theorem. That's another very long story and very interesting one. So basically, the story is because first of all you have to formalize what is a map, what it means to color a map. That requires some tinkering. So as you can see from these examples from the continents, we can definitely put a coloring on the map of countries or regions and just make sure that we can just use at most four colors, and that will be enough to color the map. But what's very interesting and challenging is that the proof of this theorem, which was done by Appel and Haken in the 70s, required some tremendous amount of computation, and these computations were essentially never accepted. So the paper was accepted in Annals after many years of serious inspection, but somehow mathematicians were still unhappy about the outcome. The mathematical part was okay, but somehow the computational part was left not completely validated. And it was just, again, very recently that all of these parts were combined together into a formal proof, and now we are completely sure that this color theorem is proved really formally in a mathematical formal system. And the very recent one, also famous Fermat's last theorem. So this is a statement that I think is probably the most prominent in this class, because it's such a simple thing. I mean, you just add numbers like x to power n, y to power n, and then you want to find the number z, which is also an integer. You can even just assume that these integers are simply non-negative. And if they sum up to the nth power, then you claim that either one of these numbers is actually 0 or n is at most 2. Okay, so that's I think that's probably the easiest from these three to formulate. Yet the proof was such a tremendous effort and such a big achievement when in 1994 Andrew Wiles presented the complete solution. Then it was noticed that there was actually a bug, and then this bug was fixed eventually. So I think what is remarkable also about this story is that the formalization, so making sure that this theorem is completely sound and the proof is completely valid, is still taking place. And it's a grand challenge led by Kevin Buzzard now at Imperial College. So people are trying to really understand if every single part of this theorem is completely sound and valid. And there are some surprises, like recently crystalline cohomology was actually being formalized, and it turned out that not all of the foundations were completely sound, so people had to rework the proofs and so on. So that's a major challenge, and I think it's a good guideline showing us that we have still a very long way to go, even with existing theorems, to get this kind of trust and understanding about like what mathematical statements are really proving. Okay, but of course, formalization is not only these theorems. We have in the last 15 years we have seen a gigantic improvement in these methods of formalizing mathematics. This is mostly based on dependent type theory, like Koch and Lean, and we have seen a lot of theorems being formalized, including also statements from group theory like Fay Thompson, and many more to come. So if you go to the website of the Lean project, which I'm going to talk about in a second, you can see like how many different things people are trying to formalize. It's not only mathematics that is being also formalized, because people are trying to also formalize software, also formalize the way the hardware works. So essentially, every organized deductive system can be turned into this kind of formalization procedure, and we can somehow benefit from that. And just to mention a little bit of history, I already mentioned the name of David Hilbert, but there's also Kurt Gödel, Alonzo Church, Haskell Carey. So these are the names that probably should be familiar to you if you get interested in the process of formalizing mathematics. All of these names are going to show up. Of course, Kurt Gödel is very critical to realize that the quest that we are onto, the one that actually David Hilbert thought about, is actually in principle hopeless, because like every time we organize a piece of mathematics into a formal system, there will be a statement. That's exactly what Kurt Gödel proved. That will be not. I mean, it will be true in every possible model of reality, but it won't be a provable statement in the formal system that we are designing. So somehow there is always a way for mathematics to escape a single given formal system if it's sufficiently complicated, like if it contains at least the Peano arithmetic, so the arithmetic of integers. You can always concoct something very strange that won't be actually formally provable in this system. But I think we are okay with this in the sense that, like, we have not seen yet, at least in the formal system that we use nowadays, the Zermelo-Frankel plus choice set theory. We have not seen many examples, actually none, I think, that would be interesting for us, in the sense that like something critical about the world that is interesting won't be provable in this system. So that's something that is worth remembering. Alonzo Church and Haskell Curry. So these are the names that will show up in a second. So I'm not going to talk about them for a moment. And I want to also mention Frick Vidic, who made a very interesting website. This website actually contains a collection of 100 mathematical facts, mathematical theorems that were somehow proved by humans at some point of the history. And he collects on this website a lot of very interesting proofs of these statements. And all of these statements are actually collected in one of these formal mathematical languages, in which we can compile them and make sure that they are completely valid. And as you can see, this list contains 100 theorems, and 99 out of 100 are already formalized completely within one of the formalized systems. That's already quite an impressive achievement, because among these theorems, you have the famous Jordan curve theorem, and one is just still missing, and that's exactly as you might expect, the Fermat's last theorem. That's the only missing on this list. What's nice about this website is that you can click, and you can actually see, sorry, the collection of all the proofs that were found, and you can also see the breadth and scope. So how different the formalizations of mathematics can be. That's also very interesting. So like we are usually intuitively talking about things which are very simple for us to comprehend. Like for example, if we have a curve and this curve is simple, it actually cuts the plane into two pieces which are connected. So that's something that even with hand waving is very intuitive for a human because we have the experience of early childs that when we use scissors, we really do cut the piece of paper into two parts. So one is this little object and the other one is the big one. But of course, to actually formalize it in a deductive system, it's an incredibly difficult achievement, and that's something we have to remember about formalization is that turning the intuition into a formal language and making sure that we actually formalized the right intuition, that's something that requires a lot of new mathematical inventions and might be very, very challenging. And I want to mention now Kevin Buzzard in particular because he's such a figure talking a lot about formalization of mathematics, launching and running a lot of projects in this realm, and he's probably one of the most responsible people why so many mathematicians are getting interested in serious formalization of mathematics. And actually, it's very interesting to go to his blog and to his website to see what he writes about this, what he thinks about the recent improvements in AI performance, doing some kind of formalization of mathematics. Sorry. And one thing I want to mention is that Kevin is one of these people that thinks that so far the AI tools that we have, the modern AI tools, are just useful helpers. So they are not yet at the level of replacing us in the mathematical discovery. Like I mentioned this diagram, and the final bit would be the superhuman mathematician, and that's still not happening with the current AI systems. And I think I agree with this a lot. But of course, there are some shades to this statement which I want to mention more in particular in the coming slides. Okay, so to start a more technical discussion, I'm going to gradually get to the level of talking about lean code and what happens with the lean code and my own experience, like with large language models. How do I think about what is happening nowadays? One thing that we have to remember is that actually turning a mathematical proof into this certificate of mathematical validity requires a lot of effort where we actually have to experience the mathematical objects in the ways that we were not prepared for, like thinking about mathematical theorems as basically as some kind of types. That's what people actually are doing nowadays. It's very foreign to our intuition. That's something that is very difficult for us to comprehend. And I'm going to show you in the coming slides that this is probably the way of doing this. But at the other end, we want to still keep some kind of intuition about the objects that we reason about. So maybe what is being born in our eyes, in front of our eyes, is a new kind of mathematics. It's a new kind of uh, mathematical discipline where people will be actually doing a lot of back and forth between intuitive mathematics, the one that we actually write about, and usually in text, and the formal one, which is like the assembly language for computer science, right? Like nobody writes, at least most humans don't write in assembly language or in machine code. We usually express ourselves on the computers on this kind of very high level. And that's exactly what we try to do as humans. But at the other end, we need this kind of formal level of verification and of the assembly language to make sure that whatever we talk about is actually sound and complete. Okay, so let me now talk a little bit the formal systems and automatic theorem provers. So I just want to mention a few. Of course, now there's no lean here because I'm going to talk about lean in a couple of slides. But just to give you a flavor of what is known, how much was done, you should just look at this list like whole, cock. Now it's actually called rock. Miser, that's something that is very close to my heart because it's a system that was originally invented in Poland by Andrzej Trybulec and still is being developed. Proof Power, Isabel, AQP, MetaMath, there is more of this. And if you look at how the mathematical statements are expressed in every single language here, you can see how different the formalization behind them is. But there is something that connects all of this. And this is actually a connection which goes into the very foundations of logic. So I think all of the mathematically trained people are very familiar with the concept of formal language in which we are expressing mathematical statements. And this formal language that I'm talking about is actually a language of usually first order logic. There are also some higher order logics. But for this exposition now, I just want to talk about first order logic. So that's something where we have predicates, we have constants, we have formulas, and the formulas, simple formulas, are turned into more complicated formulas. So form now is just a collection of basically strings that we combine from these formulas, and we only just add the meaning to all of this once we add axioms, so the rules in which these formulas can interact with each other. But what's interesting now is that this kind of language is basically enough for us to somehow encode all of the mathematics that we know so far. So that's quite a remarkable achievement of early logicists, that they somehow managed to somehow put everything that we think about into this kind of constraints. And of course, what's critical about formalized mathematics in this sense is that we have these rules of deduction which allow us to form something called the conjunction, sorry, and the implication, and we can eliminate it. We can eliminate the implication. We have the rule for introducing alternatives. So once we learn all of this, like for example in Gensen calculus, we can start building more and more complicated sentences. So these are still rules. And now here you have an example of deduction. So that's basically how you can prove formally that this kind of sentence that we have in the end is actually true. So it's true in this sense. It's provable. Okay, so that's the little subtlety behind logic, that something can be proved, then it's of course true. But the other way around, as Gödel says, might be difficult to achieve for some of the sentences. And of course, now if you look at this final sentence here, you might hardly recognize in this sentence any single kind of mathematics that you have seen in your life. It definitely doesn't look like a mathematical statement about balls that I have described, or like about coloring maps. But one thing I want you to think about is that if you have a sufficiently expressive system, I'm going to show you in a second how lean looks like. Uh, you can believe that every single statement that we are trying to prove, essentially at the very bottom, is going to look like this. So if you have a target, like you want to prove Riemann hypothesis, there is actually a formalization of Riemann hypothesis in this kind of a language. So now the challenge that we have in front of us is to actually combine the existing axioms and, oh, sorry, that's something that someone else wrote, probably, I guess. So let me turn off. Okay, some interaction. And if anyone claims that has proved Riemann hypothesis, well, in principle, they have to deliver uh, some kind of tower like this, so that we really start from foundational axioms and we can build this tower all the way up. That the final bit of this tower, the peak of the tower, is exactly the statement that is formalized and known as Riemann hypothesis. So no one can say definitely that they have proved Riemann hypothesis if they have not delivered such a thing. Okay, but I already said a few minutes ago that there is some kind of paradox, because when we think about highly esteemed and recent developments in mathematics, then people have agreed that some of the statements have been proven, like, for example, Fermat's last theorem. But I said at the same time that they have not been formalized. So, how I can be sure that these statements can be actually formalized into this kind of tower, and that we can, in the end, actually get something that is completely formal sound? We have seen this with four-color theorem, with Kepler conjecture, with Fay-Thompson, but we have not seen this with Fermat. So this is actually a running quest. So people who are experts in mathematics can somehow get a lot of intuition about how to navigate in this complicated system. And then, if enough experts get enough trust that something is actually doable, we usually publish this as a paper, and then we see that people are starting using this. But somehow, like at the very deep level, before we actually get this kind of super formal proof, we cannot really be sure about the validity of the statements that we are actually claiming. So just to give you one example, which is very which is very prominent and very spectacular, is that in Principia Mathematica there is a statement in which it's essentially proved that 1 plus 1 equals 2, and this statement is actually encoded in some specific theory which basically encodes the way we build integers as sets. And the statement really is proving this statement, in the sense that the two sets of cardinality 1, if you combine them together, they give you cardinality 2. And it's such a complicated thing to express, because, like, when you start with the very naive foundations, you can actually see that proving statements in this kind of language can be very cumbersome and actually very impractical. So to write all the steps of mathematical deduction of the four-color theorem takes like several hundred lines, or even thousands or hundreds of thousands of line of code in Coq. And this code in Coq is actually compiled into something of lower level, like on the level of type theory. So, like, once you see this kind of statements, you can see that the actual proof of any single of these theorems goes into millions of lines of code. So that's definitely something that humans cannot comprehend. And I think this is the most interesting part, because now, as I said in the beginning, we want, in some sense, to keep very high intuitions, but somehow have the precision of a surgeon to somehow navigate in this complex environment precisely at the level of every single operation that we can conduct from deductive logic. But now there is a miracle that I want to talk about, and this miracle is actually connected to programming, or to lambda calculus. So lambda calculus is an invention of Alonzo Church from the 1940s. It's a very beautiful theory, which was invented to talk about programming, about computability, about Turing machines. So all these notions that are related to computations. And the concept of lambda calculus is that we actually have a very intuitive notion of a type. So type is something that we can connect nowadays with, for example, a variable. If we program in a programming language, we have a lot of variables, and they have different types. They can be strings, they can be integers, they can be some complicated objects, and so on and so forth. And lambda calculus is a way of somehow playing with this idea of types and producing new ones from the old ones. Like here, you have a very prominent example where you have two simple types, and then you turn this into this composite type ROB, which should be somehow connected in our mind with the classical notion of implication. And why is that? That will show up in a second. But maybe an intuitive way of thinking about this is that if you write the truth table for the implication, you can notice something remarkable that if you put the true values, then 0 implies 0, that's okay. 0 implies 1, that's okay. 1 implies 1, that's okay. But 1 does not imply 0, so that's one of the truth table false values. And if you turn this into this language of types, you can think of this in the language of functions. So like if you have a function, like something that takes an element and does something to this element and sends it to something else, well, how we can actually build a function from sets? Well, if the set is non-empty, then there is always an example of a function. So if you have two non-empty sets, we can always form a function. So that's somehow the intuition of one implies one. If we still have an empty set, uh, then because we have nothing to choose from, okay, then we can still form such an empty function. It's just a single object. But the other way around, if we have a non-empty set and we have an empty codomain, then this is actually impossible, because if you have a non-empty domain, that means that for every single element from this domain, we have to attach it to an object in the codomain. So that's impossible if the codomain is empty. So in this intuitive sense, one implies zero is actually false. And I like this intuition because it shows you in this kind of very naive sense, like what is really the bridge between mathematics done in this formal language of deduction types and the lambda calculus. So there is actually a very interesting magical bridge between formal logic and formal lambda calculus, which allows us to carry the intuitions from logic to functions. So functions are kind of expressing the intuitions of logic. And what's remarkable is that the only thing we need on top of this is the rule of abstraction, in which we can form something called the lambda function, so that it's a function with a variable, and that this variable can control certain values. And now, if we have functions, they have one property which is vital here, is that we can compose them. And if you can compose functions, then we are actually on the level of the rules of lambda calculus. So we have the rule of variable, we can introduce a variable. We have a rule of abstraction and assignment. And now if you have all these rules, you can actually see that if you start from very foundational statements, you can build up a particular function. So this is the function that you get in the end. And this composed function of three variables, it actually has a remarkable property. It has a type, and the type, so that's something that this function produces in the end, is actually the statement that we have seen in one of the previous slides. Okay, so now what is really going on? So I just showed you in this kind of very simple crash course that you have two ways of actually looking at mathematics. So one way that I showed here is actually called the rules of logic, deductive logic. And actually, if you are very unhappy with this, well, you can turn this into the rules of lambda calculus, of producing functions. And miraculously, these two things are actually equivalent. So this is the content of the famous Curry-Howard De Bruijn isomorphism or correspondence. So basically, the language of logic and the language of lambda calculus are essentially equivalent. Okay, so now think about the implication. This is quite deep. So if you have a constructive way, in the sense that you have a proof which can be completely formalized in the right type theory or in the right logic, you can actually write it down, and the verification, so the process of making sure that we build this tower, can be turned into a computer language in which the validation, making sure that the statement is provable, just requires us to build a compiler for a specific language in which the compilation process, so the process of assembly of the complicated functions, can be completely automatized. And once we know the target, so once we know what we want to prove, so this is called the formalization of the statement. And now we are on a quest where someone has to write a program. And if you write this program, then you're done. If you have done a program, that means that equivalently you have completely proved your theorem. Okay, so this is very profound, because now it shows us that mathematics perhaps can become, at least this constructive part of mathematics, where we have statements without any controversy. We can explicitly construct the proof. We can explicitly make the lambda functions. It can be really turned into part of programming. You can program mathematics in the most profound sense. So like, if you have a proof, you actually are a programmer writing a particular lambda function construct. And if you have proved something, then the only way to make sure that you have really proved is just to be sure on this foundational level that you have constructed the right type. Okay, but now I want to show you in the remaining time that this beautiful dream that I'm talking about is actually very complicated to build, and it's actually not so easy to fulfill all these wishes that we will have documentation for all of the human knowledge, for all of the proofs that we talk about, that we can scale it up to the level of proving Fermat's last theorem, maybe something more that we have like on the list, maybe discovering something completely new. So that's something I want to address. And as you might expect, there will be some kind of artificial intelligence in the picture. But I'm going to show you that there's still a long way before we actually get to this realm that everything will be completely automatized. So before I get into AI, I want to mention a very curious example, which was way ahead of its time. It's called the Robbins conjecture. This is some beautiful fact about formal algebra. So everyone probably is familiar with the concept of the Boolean algebra, but maybe not many are familiar with the concept of the Robbins algebra. It's just a different type of equational algebra where you have axioms, you have some kind of equalities that hold, and you want to prove other equalities. And the conjecture that Robbins actually came to was that the different axiomatics for Boolean algebra that he found, the question was like, is this axiom that he found, the so-called Robbins axiom, giving you exactly Boolean algebras, or are these Robbins algebras actually something else? So that was the question, like, is this two different types of axiomatizing Boolean algebras actually equivalent or not? And it turned out to be true, but the only proof that we know as of today, it was actually found by William McCune, and actually William McCune didn't find the proof himself. He actually wrote a very interesting piece of software that was basically exploring the complicated tree of equalities in the system. And after around 9,000 steps, it actually found in this final substitution a complete proof that the Robbins algebra is a Boolean algebra. So that was quite remarkable, because it's one of the very earliest recorded in history examples of mathematical statement. I'm not sure if this is such an interesting statement per se, but what's interesting is that the proof of this claim was really designed by human, the software, but the proof was actually found by computer. It was not not a complete brute force. It was some kind of very interesting deep search, and it actually shows us that mathematics can be done in this formal way just by computers themselves. So we can be like as much out of the loop as possible in this case. So people were inventors of the theory, but no human actually made any direct act of invention in the proof of this statement. The proof was actually simplified recently. So I think that the shortest version of the proof is just 15 pages. And that's quite remarkable because it's such a pure statement. There is just a lot of substitutions, and that's it. There is no, I would say, deep meaning. There's no structuring in this proof. So if you think about mathematics, I think this is a nice example to think about, because it shows you that maybe in the end, the things that we are going to prove will be like this kind of game. It will be like the game of Go, that you have to prove some steps, and maybe machines will help us. Like it was famously with AlphaGo, the rule the move 37, and maybe something that the machines will do for us will be inventing this kind of moves 37 for all of mathematics, and we will be just appreciating that something that has no consciousness, no emotions, no, I would say, self-reference, can still be useful for mathematical quest. Okay, but to make it work, there's a very long way from the 1990s to nowadays. What happened, and now I want to capture in the in the last few minutes some of the very recent developments and somehow interactions that happened in mathematical world and AI. So maybe one of the most prominent recent examples of this formalized mathematics is something that is known as Feynman-Ruzha polynomial conjecture, that was recently proved by Gowers, Green, Manners, and Tao. And that's a remarkable example because it's just a mathematical fact that can be written in a very simple way. It's a fact about covering sets in a finite vector space. And the proof was actually offered by humans, but the verification that happened afterwards, that was also made by humans, is completely making sure that everything is sound with the proof. But the graph somehow shows us that there was a real effort here, and the formalization that happened was not so straightforward, but it was still, oh, oops, sorry, went too far. But I'm going to show you now in a few minutes that this kind of graphs and verifications can now actually happen just on the level of computers. So we don't need humans all the time in the loop. Okay, so to introduce these very recent developments, I want to advertise the Lean programming language. It's a remarkable language that was developed mainly by Leonardo de Mura, and there is a huge mathematical community behind this language now, which is developing some kind of uniform mathematical library called MATLib. It's an active community, so if you go to Zulip channel, you can collaborate, you can interact, you can help people. One of the goals that this community has is to actually somehow unify in this single library all of the developments of mathematics that people made, so that like if there is any new mathematics coming, like in the form of a statement that you want to prove, you want to be sure that all of the definitions needed to express this statement are already in MATLAB. The foundational theorems, the lemmas that you are going to use, like for example for this Gursat lemma, everything was somehow already contained in MATLAB. So that's why the proof is so straightforward, because you are just using the tactics and the constructions that are already formalized in Lean. So that's good for you. Okay, but now if you go to the level of mathematics, which is very complicated, there was actually very recently an experiment done, introduced basically by Peter Scholze. So Peter Scholze was interested to formalize his very recent theorem with Dustin Clausen And I'm not going to talk about this theorem per se. It's a very interesting fact. But what's even more interesting is that it took 1.5 years and several people, including Johann Comelin, uh, to actually completely express and formalize this fact. So it was all done in Lean. So that shows us that even the very recent and modern mathematics can be completely formalized in this kind of formal language. That was still done by humans. That was like 1.5 years ago. I remind you that 3 years ago we had the revolution of generative AI, which is now able to program. So that was still like before this really happened. And now I want to show you that there is something interesting at the verge of these two fields that is happening at the moment. So I'm going to briefly talk about this as well. And of course, to what is artificial intelligence? Well, we could talk about this for hours. I'm not definitely not an expert in this field, so I just want to mention some very simple observations. Like essentially, artificial intelligence emerged from the invention of the McCulloch and Pitts neuron. That was later renamed to perceptron of Rosenblatt, and it's such a simple invention. It's just basically something that allows you to realize the following idea. If you have two data sets and they can be separated by the line, you want to optimize the position of this line so that if you get a new data entry, you'll be able to tell whether your data entry belongs to one set or the other. Like in this case, you want to tell between cats and dogs, and these entities are measured in some kind of abstract way by the number called domestication and the number called size. And of course, if you think about the problem of finding this separation line, that's exactly what the perceptron or the neuron really is. So you have some abstract real numbers. You multiply them by weights, you add them together, and then you have this summation function. And this summation function then gets activated. So if something lives above the line, right, which is exactly when the inequality is like, say, bigger or equal to zero, right, then you get one class, so you get some kind of activation. Or if it's below the line, you get another type of activation. And that's essentially all. So that's it. So that's the perceptron. Now, of course, from the 40s and the 50s, where these notions were invented to just basically address the issue of why people can actually think about abstract logic. That was the original motivation. It took many years for people to realize that this can be actually used for some good, and that this good is actually known as neural networks. So neural networks are basically an idea where we combine together all of these notions. Like we have one perceptron, the output can be turned into the input of the second perceptron, and so on and so forth. And then you can organize this into a massive network where everything somehow gets combined into this huge neural nets, and then we can separate like more sets. We can do this kind of generative thinking, generative ideas, and so on. So it builds up, but like internally it's just built on this very foundational, very simple layer. Of course, it's not so easy. Like the most difficult part about neural nets is that if we want to use them for something useful, we have to train them, and the training is something that we basically do with linear algebra and with data and some kind of policy reinforcement learning, and back propagation and gradient descent. So there's like a lot of very foundational mathematical technology that goes beyond this. And suddenly, if we combine it in the right way, we get things like LeNet. So that this is the neural network that can basically tell different numbers just from how we draw them. So we have to teach it. This is how it works internally. This is taken from Three Blue One Brown. That's a remarkable website where you can learn about, for example, neural nets and other mathematics. It's on YouTube. Uh, and now I'm jumping quickly to the conclusion. So we fast forward. We have large language models, and these language models, it's just something that is entailing this idea of neural nets inside, and somehow combining together it allows us to basically write text. Okay, but if you can write text, you can probably also write text which is structured, and that's exactly what happened with ChatGPT in the 22 and 23. So somehow we got neural nets that were able to write text which looked like programs, like Python. But now, if you have Python, then you can say, okay, maybe we can write more sophisticated programs. Maybe we can train these networks to somehow write more and more sophisticated programs on every level. And here we come to the invention of interactive theorem proving with AI. So now we are on the level that we not only have neural nets that can somehow produce new tokens, new text, but they can produce a text that resembles the meaning of the formalized mathematics. Now, what's very interesting about this paradigm is that we can combine this paradigm with the verification software. So the software that compiles mathematics and tells you whether the text that you have written is correct or not. And this is something that you can use for training. So now, if you train your mathematical models, your language models on this kind of paradigm, you get really very quickly to the level of having language models that basically hallucinate. I like this word because it's like it's emphasizing the probability behind this. So there's like a probability distribution of generating new statements, new mathematical theorems, and by chance, if you train it on large data corpuses, you can actually get these systems to prove new mathematical statements. That's exactly what's happening nowadays. We have some prominent examples that were even trained without human intervention, in the sense that there is no prior human knowledge in the language model that lives behind alpha geometry. It was completely trained on its own experiments. That was actually very interesting. Like the model was basically trained on some kind of deduction in Euclidean theorems, and the effects were quite remarkable because these theorems that the model can prove were on the level of International Mathematical Olympiad. That was last year, and I was very surprised when I saw it myself, because I said, like, this is definitely not just brute force, because in these systems you have something like 50 or 60 different tricks, and the theorems can be as long as like 200 steps. This is how internally this looks like as a system. So every time the model has some kind of derivatives, it can try to build like this kind of logical envelope for the statement. If it fails to prove the sentence that it's interested in, it's actually running the language model, and the language model is generating a new token, and the new token in this case is just a new mathematical construction that it does, and then it repeats itself until it hits a solution or not. And this year, we have seen that these systems were actually expanded to address International Mathematical Olympiad as a whole. So not only geometry, but also other types of statements. Most of them, like including geometry ones, were for this year were completely formally even proved. So there were several teams that did that. It was one team was from OpenAI, the other one was from Gemini, another one was from Harmonic. So recently we have seen more teams coming in. Also, International Programming Olympiad (IOI). That was also something that these models address. So there is like a lot of recent development in this direction. I just want to, in the end, and maybe for the start of the discussion, I want to show you, like, what are the secret ingredients behind this success, and is it really something that can scale up to the level of research mathematics? Of course, there is some kind of technology behind this, and this technology is so far mostly related to the reinforcement learning. So this is a way in which you fine tune, you reinforce, learn, teach this system to behave nicely on the long string of thoughts, and you're somehow improving the system if it's correctly deducing the steps of the proof, not only the final answer. But of course, it's very difficult to measure this. And I want to personally also connect to this story so that somehow measuring how these formal systems and how the language models are addressing the issue of mathematics is very challenging because if we are just asking for very simple questions, maybe we are just deluding ourselves that there is some progress and these systems are making really progress, but they are not. And that's somehow how I got involved into this frontier math tier 4 project with Epoch AI. So there are 30 of us, more than 30 of us, and we were trying to find out whether some of the most prominent systems, like including ChatGPT and Gemini, we can actually solve mathematical questions, but actually without making sure that they have a formal proof. And what surprised me in particular was that already in May of 2025, we have seen models which were able to even solve this kind of very complicated question about modular forms. That was exactly the what O4 Mini model did for us. It derived everything, including the final formula. It couldn't compile everything because it couldn't run Sage, but it really did its best. It's still not a formalized mathematics, so you might think, okay, maybe there is some gap, maybe there's something here that basically tells us that, oh, maybe this system is just pretending to prove something, and that's actually something that is quite a lot the case recently. We can see that the systems are sycophantic; they are just trying to please us. They are just trying to convince us that they have proved something, but maybe they don't have a proof. So in some cases, it does happen. Like in this case, we actually did see the real proof inside the trace of the system. Sometimes they don't. You can trace actually the the results on the leaderboards of Frontier Math. I think this is already not up to date. So there were some updates recently, like up to 20%, like 9 out of 48 questions were completely solved. By completely solved, I mean like the models derived the right number in the end. But did they derive the right proof? Not so. So sometimes it was a complete proof, almost complete proof. There were still some gaps, but it's not always the case that they deliver exactly the formal proof. And now I want to finally finish with some kind of ideas for the future. So is this really a beginning of a new era? Are we going to see enhancement for mathematicians, that we are going to somehow improve our thinking? Well, I was a bit skeptical quite a few months ago, but recently I got involved into trying very recent systems that somehow relate to coding. So one of the most prominent ones recently is Alpha Evolve, which by itself, by writing computer programs, was able to somehow prove very interesting statements in mathematics. It was still like an improvement over something that people did, but still it was an improvement in the sense that they were optimizing some result in mathematics that was not known before. That was quite remarkable. Okay. Oh, sorry. Where are we here? Okay. And okay, so I want to get to the punchline of this. Okay, so this post AI mathematics that I want to mention relies on one very interesting fact, is that we are humans and we cannot read all of the mathematics. What you can see here is just a map of how archive looks like if you make a language embedding of every single paper. And this is something that I want you to keep in mind, that if you're talking about the progress that the AI systems are doing, just keep in mind that these systems are capable of interacting and reading all of the mathematics that you see in this picture, while you might spend your whole lifetime just working in this little bubble here or there, and not be even aware of all of the big things that are outside of your bubble. So if you're asking questions to these models, just keep in mind that maybe what the models are just still doing is just connecting to the existing mathematics that is just basically beyond your bubble. And let me finish with a few thoughts about formal systems that I'm using nowadays. It's It's a very recent story. So Alpha Scientist, this is more for like general science. There's the new version of this AI Scientist by Sakana. But I want to prominently mention also some systems for mathematics. One is called Aristotle. There are several of these systems. Recently, there's Kimina, Numina, and Gauss, and Seed Prover. There are like really several systems that are basically operating on this level. That there is a language model, and the language model has some kind of an extra ingredient that allows you to build mathematical proofs just like in lean we were writing so far, but it's mostly done automatically, so the model is actually guided by human instructions, but in the end it just produces completely verified statements that we can then look into. And how this looks like, well, I think it's best if you want to get your experience, you can sign up to Aristotle, but you can also just go to the website. If you have a phone, you can go to the website of Kimina Prover, and then you can put your own statement here in the box, and Kimina Prover is going to formalize it for you in Lean. That's something that you have to verify if the formalization is what you intended. That's one source of the issues that might happen, and then you can see actually the model basically hallucinating all the steps of the proof. And once it hits on the level of the language model, the conclusion, it starts producing a formal mathematical proof. So this is the formal proof written in Lean. And then in the end, the system is actually compiling the proof itself. So that once you get a green tick in the end, you know that you actually got the proof of your formalized statement. I think this is quite remarkable. So you can have like this kind of very interactive experience. It's still not scaling up very well, so I'm going to address it in the questions. That to actually do it for all of mathematics, that's exactly what we would like to intend here. Well, there's a lot of stuff for training and for scaling up definitions. There's like a huge amount of work that has to be done, but in principle, it's doable. And I think it's quite remarkable to know that these kind of systems that were just invented this year, they already exist and you can interact with them and play with them and have some fun. Uh, Here's another example I want to show you. That was an experiment I ran myself very recently. So I designed a kind of a theorem, which basically was a puzzle. So I managed to somehow turn this puzzle into a hallucinated proof with GPT-5 Pro. I didn't trust the proof itself because indeed it contained some gaps, some little gaps. So what I did afterwards was to actually turn this into a formal proof, where I'm going to show you in a second. We have a lot of examples like this recently. There's also the alpha proof system that is being developed by Google DeepMind. That is still on the launch. There's Aristotle, as I mentioned. So for Aristotle, I'm going to show you one example. And there's also Math Inc. So Math Inc. recently managed to, with the model called Gauss, to complete the proof. This is the full picture. Find all of the formal statements and proofs for the prime number theorem. That was a project run by Alex Kontorowicz and Terence Tao, and they got stuck because they lacked humans that could somehow help them formalize this, and Math Inc. somehow managed to fill all the gaps. So somehow the AI system managed to complete the task for them. And also, maybe if you follow Twitter, you could see on X a lot of these developments. Like Boris Alexeyev recently was completing a lot of proofs, actually with combination of Aristotle and his own invention. And that's quite remarkable because we have now formalized proofs of these statements, completely written in Lean. Here's one example which I started introducing, and now it has a complete circle. So I started with a prompt. So I'm just really the inventor of the prompt itself. ChatGPT wrote for me, I would say, the blueprint for the proof. I didn't trust it yet, so I turned into Aristotle, and Aristotle actually, in one shot, turned all of this into a valid mathematical proof where I could just compare the sentence. saying what exactly was formalized. It was actually simple in this case because it's just a group with a specific presentation, and it's going to be just a group S12. So it's very easy to somehow get things done, and it was done automatically. So I don't feel even as completely as an author. I feel like an author of the prompt, but not the author of the paper. So that raises a lot of questions that I think in the future we should be talking about. That's a very recent other example where I generalized this picture. So I basically encoded the picture in the system, and then again, with the assistance of Aristotle and ChatGPT, I turned all of this into a proof. What's remarkable is that the previous case could be basically turned into computer algebra exercise, but not this one, because in this one you have infinitely many cases. So these long strands that the group is rotating, these cyclic subgroups, they can be of arbitrary length, and the system suggested to me first which of the situations can happen, and then I finally formalize everything in Aristotle in 3,000 lines of code. That's I think for me it's one of the most spectacular examples that we can design mathematics on a very high level, and then everything else can happen on the level of programming without much human intervention. I think it's pretty shocking that that something is from last week. And final bit I want to show is this problem of Erdős 1026 that was featured recently in a blog by Terence Tao, where he very nicely explains that somehow the intervention of humans and interaction with AI systems finally allowed to get the final conclusion. That's the final conclusion of the conjecture, some kind of bound, and everything was proved with computers and verified in the end by humans, and also humans gained some insight from this. So I think we are really on the verge of something very new, and I think it's a good point to stop. Thank you very much.
Thank you for the extremely informative talk. And if you, for the audience, if you, in the interest of time, and if you have any questions, please put them in the chat, and we'll try to ask Bartos. Can you hear me still, Bartos?
Yeah, of course.
Okay, so I'll ask the first question. There are many actually interesting questions for you from the students and the from all over Vietnam. But I want to start with a question about Poland. So you mentioned that Misa was invented there, and you are now moving to a center, the Reliable AI Center. So the two countries has a shared, geopolitical history. So a lot of people here are interested. What's going on in Poland in terms of how the mathematical community, is reacting to AI, and how the government is investing in it, and can you share a few information?
Well, I would say that the landscape is very diverse, because as you know, we have a lot of very bright computer scientists. Some of them prominently even founded OpenAI, like Wojtek Zaremba and Jakub Pachocki and Szymon Sidor and Oleg Mondry and so on. We have a lot of very talented mathematicians. I don't see yet like a lot of convergence on the level between computer science and mathematics. That's slowly happening. I talk to my colleagues, and I think maybe until I would say like a few months ago, most people were, especially in mathematical community, were not very certain about whether the language models are going to be a thing, because I mean, like when you interact with these language models, you can see that they do a lot of bugs, a lot of hallucination. It's not clear whether they can be used for some good, and then if you really try hard you can sometimes improve on them, but then there's like a lot of human work. So I think with these very recent AI systems that actually do formalize mathematics, I do see some movement. So like people are getting really interested because they see like, oh, okay, so if we can produce a certificate for a mathematical statement, that's a big thing, and I think that that's something that is really happening in the last few weeks. But of course, it's still so fresh that now suddenly a lot of mathematicians realize that, oh, there is something called lean, right? And then we have never bothered to do anything serious about formalized mathematics, and I think for them it's actually quite funny to realize that now they have to learn completely new paradigm of mathematical infrastructure. And on the other end, like we have a lot of experts working on the language models, adapting them to business, to industry and so on. So I think we are still like just before this moment that I hope that somehow the mathematical community will be somehow infueled by the engineers, and we are going to see like a big movement in the direction of mathematical formalization. But just to keep in mind, there is this factor of humans putting something in the loop. Like I mentioned, that we need to formalize stuff, and to formalize stuff, we need to formalize definitions. So I see that we need to do a lot of work on the level of somehow encouraging people now to use formal systems to even turn the very foundational definitions into something very useful. I have put myself some effort into this. Can show you just for a second. So recently I was experimenting a lot with like formalization of mathematical papers, and just as a proof of concept, I took a paper of my colleague, which is just like an archive paper, and basically by playing with Lean and with Aristotle, I managed to completely formalize his proof. So now you can actually even inspect exactly the theorem itself. You can go into the theorem, everything is formalized. You have a formal proof in Lean. You can inspect the proof itself. So that's, I think, pretty cool. And I would expect that like this kind of things should start happening in the future, but it really takes a lot of time. So in my case, it was like several attempts trying to scaffold, the system with the original theorem. It was not very difficult on the level of programming Lean, but of course, it required a lot of inspection to make sure that everything is sound and complete. There are no stories, there are no hidden axioms that I'm just assuming. It's just the standard mathematics behind. Everything is compiling completely in the Lean compiler so that you can actually go through the whole proof. It's like you can see it's a paper which is like 10 pages of elementary number theory, but in the end you end up with 5,000 lines of very dense Lean code, which is completely explainable on the level of every step. But like because it uses this kind of high level tactics, so I didn't talk about this much, but the tactics is a way to somehow hide a lot of steps in the Lean proof, so that like on the level of type theory you're doing like a lot of steps, like you can do like 20,000 steps, and on the level of like this high Lean code, it can be just hidden behind like something called the tactic. Like I think the most spectacular recent one is called grind, where you can hide like a lot of algebra manipulations which are very tedious but can be done very quickly with computer algebra, and this can be turned into a valid type certificate just behind the scenes. You are not seeing this, but everything is completely documented and completely validated. And so, like, if you think about this proof, I would say this is already high level proof, right? So it's something that maybe it looks a little bit tedious for us because you are assuming something, you're doing like rewrite the theorem by the axiom and so on. But still, it's already a high level proof. I feel that this is something that we should get engaged into. So like get acquainted with the systems and try to document as much mathematics as possible. Of course, with this final bit that we need to verify exactly whether we have formalized what we have intended. That's something I showed with Kivina, and that's something that also happens with Aristotle. We don't want to misformalize, right? It's a different proof to show that a square root of an integer of a positive real number exists in real numbers, right? And it's a completely different proof if you do it over algebraically closed field. And these two things have to be formalized. But now, if you are asking for a specific version and you are going to use this specific version, you need to know that the type of the theorem that you're encoding is actually valid, is actually correct.
Very interesting. Wow, that's fascinating. And I'm going to combine two questions from our students, one of them in high school. So, how do you think this new development would change the way we do mathematics, and especially for the role of graduate students? Um,
Yeah, so I think so. I get a lot of these questions recently myself. I also get involved into discussions on X about this. So my stand is that actually I don't think mathematics is going to end soon in any reasonable sense. I'm virtually in Vietnam, so I want to bring to people's attention the famous work of Ngo Bao Chao about the fundamental lemma. It's a paper which is 150 or 160 pages of very dense mathematics. Now you could say, okay, Bartosz, let's take this paper, right, and then let's put it into Aristotle, and let's try to formalize it. I would say, okay, let's give it a go. But then when you try, you are going to see that this is, like a flower. It's just opening up. The moment you zoom in, you can see like on the level of big picture, it's just, it's like a beautiful flower. Then you zoom in, you have all the cells, all the mitochondria, all the organelles inside. And on the level of mathematics done with Lean, you have to somehow invent the biology. So in this sense, the logic of how to prove all this stuff. And there's so much beauty in doing this kind of mathematics. So I don't think so first of all, I don't think inventions are going to end. So these systems, as you can see, they can be instructed to do something, but if they are asked to somehow run in the wild and generate some new value, some new quality, I mean, they are clueless, right? They can replicate human inventions. I mean, they can generate statements that they can prove, but then they cannot. They don't have a judgment. I think this is quite fundamental. So for the young people, I think what should be realized is that mathematics, as we train it, as we train professional mathematicians, we train humans to make beautiful judgments. Like we interact with the world and we can see something like, we see the sphere packing, but now everyone can intuitively see the sphere packing, but not everyone can successfully formalize it into some kind of a game and gain insights from this to the world. And that's exactly where mathematics is happening. I think recently there was a very nice talk by Akshay Venkatesh, where he was exactly talking about the same issue that if you look, for example, at the tilings, it's very intuitive to play with the tilings. Like there was a recent development of one of the famous problems by Hilbert about tilings, and it turned out that there exists an aperiodic monotile, and the way this monotile was found was actually very human, very, I would say, very intimate. People found the shape just by some kind of very deep intuition. Everything else can be now formalized and can be proved, and machines can help us with organizing all this knowledge. But somehow, the very act of turning the intuition and the insight into proper mathematics, that's something very human. And I don't see it yet in the systems. So, definitely studying mathematics probably is one of the most interesting engagements in 21st century, and I definitely encourage the young apprentices to get into this because it's going to be a fun quest.
are there any other questions? You think?
Perhaps I have a question. Hello, can you hear me?
Hello, Bartosz, can you hear us?
Yeah, I can hear you. Yes.
Go ahead.
Yeah, so actually this sounds beautiful, but in reality, I have a following problems. So me and my colleague, we published a paper and we put it on the archive about 2 weeks ago, a paper, and then 1 week later there was this guy who published, put on the archive again a paper that is kind of proving a very similar theorem to ours. So I read the paper, and it seems exactly what he's doing is he put our paper in the archive. I'm sorry, in the some kind of AI system, and it created a 25 pages long paper with beautiful introduction. And but the theorem statement is completely rubbish. And but so I can imagine that this kind of thing will be very, that we will see more and more of this kind of rubbish on the archive and in many other, possibly journals in the future. So how do we, prevent this situation?
Yeah, so I think what you're referring to is like this experience that I mentioned here. So that like let me show you again. Uh, so once you ask a system like ChatGPT to give you something like a proof, you do get a text, right? And then this text might like remarkably look like just basically a mathematical theorem, and then you can be deluded that you actually proved something.
Yes.
So I think the answer is actually combination of the two, right? That's something I mentioned with Kimina, and I think this was the very nice toy example to show. So what the language model is actually trying to do for you is this box here, the middle one, so that it's just like producing some kind of ideas like how to prove the theorem. And then you have if you specify what exactly are you proving, right? That's I think that's basically the essence of how we should validate mathematics. Like if you and the other authors would agree exactly what is the formalized version, like I showed you here, like what is the formalized version of the theorem that you are trying to prove, then no matter whether it's a ChatGPT or it's another system like Aristotle or something else, it's going to derive a proof, or a human. Like if in the end you actually have a formalization of your proof that compiles, then this is really the only way we can make sure that whatever we produce is actually valid and sound. Now, of course, the paradox is that for the last basically hundreds of years, the effort of producing a mathematical proof was just a human in the loop, and now we have all these systems that cheaply can produce a lot of text, and I think the effort is moving now towards how we can actually formalize. If we cannot formalize, that's a very big issue, because I wouldn't trust an mathematical insight that was basically just produced in this way that I mentioned here, so that I go from a prompt to a text, and that's it. Because the systems, the AI systems are built in such a way, as I mentioned, the second fancy, that they try to please you. So they try to please you with reaching the goal. So they are going to cheat. We have seen this in the AI benchmark, this frontier math, that sometimes so the model, the only purpose for the model is produce a huge number, and if the number is reached, then we get some kind of insight that, oh, the model probably has done all of the good work, because otherwise it's unlikely to come up with this number. But with mathematical statements which are not benchmarking ones, like for example this one, like convince me that this statement is true, there is so much place for the interpretation that basically everything that is generated with AIs, with LLMs, I would say it's like outright rubbish, right? Of course, it could be a helpful rubbish, and it usually is the case that we can use it for some good. But now we really need the effort of actually formalizing it, documenting that it's really proving the point. And once we have the formalization, then exactly we can trust that something happened. Notice that that example that I showed very early today. It was this Freiman-Ruja conjecture. So that was something that was formalized by humans. And I would say that, I mean, with human proofs, maybe we have a higher confidence that something is valid. With LLMs, we should have lower confidence because they can cheaply produce something that is devoid of internal logic. We have some kind of internal logic built into our brain, so we are not trusting every kind of insight that these systems are producing. But I think it's in the end it's the same game. So if we don't have a formal proof, we cannot trust neither humans nor LLMs. So I think there should be definitely some kind of I would say gradation here, that if a proof was generated by LLM, it's more likely to fail because humans are objectively still much better at producing long theorems. But there's always a risk that if it's not formalized, it's still false. So I think two issues is like this AI slop. That's everything that AI is producing might be garbage. But there's also the formalization issue. Are you formalizing the right thing? You can also misformalize. You can hide the axioms. You can do a lot of nasty things. Maybe the compiler is not correct. That's another issue. So I think we are entering now an area where we will be struggling. There will be like an influx of ideas from people who are not even professionals that will just run the systems, and we will have to somehow handle it. My answer is that we should put a lot of effort into scaling up this formalization part, but this will be like a tremendous effort, and that's something we cannot avoid, definitely.
Yeah. Thank you.
Yeah, yeah, I think it's very true that we only formalization can let us automatically check both human and machines, but it has to be done the right way. I think
Yeah.
it's the right. But thank you very much for your very energetic presentation and discussion, and I think we've
Thank
taken a
you.
lot of your time already. So yeah, thank you very much
Yeah.
for
Pleasure.
the talk.
Thank you and have a good holidays.
Thank you. Bye bye.
Christmas. Yeah, bye bye.
Thanks. Wow. Bây giờ nó cũng làm được glamour